Okay, in today's lecture, we're going to start our Chapter 4 material on vector spaces. And in this first part of the Section 4.1 material, we're going to define what is a vector space and look at some examples, some classical examples of vector spaces. And then in the second part of this section, we'll introduce something called a subspace. So let's start by defining what we're going to be working with throughout this Chapter 4 material. What is a vector space? Well, a vector space is any non-empty set, which we will use capital V to denote, of objects which we will refer to as vectors. So when we talk about vector spaces, the objects within a vector space may not be vectors in the conventional sense that we've been thinking about them. Now this non-empty set of objects called vectors is equipped with two operations which are referred to as addition and scalar multiplication, which are subject to 10 axioms or properties which are listed below. Now, when we go through these properties, let's keep in mind that these axioms or these properties must hold for all vectors u, v, and w in our set V, and for all scalars c and d that we're going to use in these in the statement of these properties. So the first property that a vector space must have is that the sum of two vectors, u and v, in the space, which would be denoted by u plus v, must lie in V. So we say here that V must be closed under addition. If I add any two vectors in my space, their sum must also lie in that space V. The second property is commutativity of the sum, that is, u plus v must equal v plus u for any two vectors in our space. The third property is associativity of the sum, which says that if we are adding u, v, and w, we could take first the sum of u plus v and then add w, and that would be equivalent to taking the sum of u with the sum of v and w. Now, property 4 is the existence of a zero vector. So there exists a so-called zero vector, which is denoted as boldface 0 in our space V, such that if I take the sum of u with 0, it's the same as the sum of u 0 with u, which leaves me with just u. So there exists some vector such that if I add it to any vector, I get back the original vector u. Now, property 5 says for each vector u in the space V, there exists a vector denoted as negative u in the space V, such that the sum of u with the negative of u, regardless of the order of our sum, would get us back to the zero vector. Now, the last few properties all have to do with the second operation that we're defining on our non-empty set, which was referred to as scalar multiplication. So here, the first property dealing with scalar multiplication, property 6, says that the scalar multiple of some vector u by a scalar c, which is denoted as c times u, is in V. So that is, our space V must be closed under scalar multiplication. If I take any scalar and any vector which lies in my space, the scalar multiple of that vector must also lie in the space. If that is not true, then my space is not called a vector space. The second property is the distributive property for scalar multiplication, namely that C times the sum of u plus v is the same as the sum of the scalar multiples cu and cv. Similarly, in property 8, if we have a sum of two scalars, c plus d, and we're taking that multiple of u, that's equivalent to the sum of the scalar multiples cu and du. Property 9 is an associative property of scalar multiplication, which says that if we multiply the scalar multiple du times a scalar c, that's equivalent to taking the product of the scalars c and d and then multiplying by u. And our last property, property 10, is that 1 times u, that is the scalar 1 times the vector, times any vector u, must give us back the vector u. So this is the definition of a vector space. Any non-empty set of objects with two operations known as addition or scalar multiplication, where all of these 10 axioms or 10 properties hold. Any set with operations that does not fulfill these 10 axioms is not a vector space. Now, making use of these 10 axioms, we can establish that the zero vector and the negative of any vector are unique. So here, we can show that the zero vector, which is discussed in axiom 4 above, is unique. That is, for any vector space, there is only one zero vector. And the vector negative u in axiom 5 is unique to any vector u in our space. That is, each vector u within our vector space has a unique negative, an additive inverse. So let's see if we can establish one of these results for uniqueness, at least one. So let's see if we can establish uniqueness of our zero vector. So let's suppose that we have two vectors. I'm going to call them z1 and z2, which will be zero vectors in some space V. Then I know if I were to take the sum of z1 plus z2, that would be equal to just z1. Now that follows from axiom 4, because the sum of the zero vector with any other vector must give us back the indicated vector. So since z2 is a zero vector, the sum of z1 with z2 must just give me back z1. That applies or follows directly from axiom 4. So we can say here, since z2 is a zero vector. And if I were to take the same sum, z1 plus z2, that must also equal to z2, because z1 was a zero vector, and by axiom 4, the sum of the zero vector with any other vector in my space must be equal to that other vector, in this case z2. So here, since z1 is a zero vector, and now we have the value of z1, which was equal to the sum of z1 and z2, must be equal to z2. So here, z1 is the sum of z1 and z2, which we've shown is also equal to z2. So z1 must equal z2. Therefore, we've shown if we have two zero vectors in any space, they must be equal to each other. That is, there is only one zero vector for any vector space V. Now, the uniqueness of a negative or an additive inverse for any vector in a space follows pretty similarly. We can make the assumption, let's say, that we have for a given vector two additive inverses, and by making use of the associative property of addition, that is axiom 3, as well as property number 5, we can show that that additive inverse is unique. All right. Now we can also show the following. So for each vector u in a space V, and for any scalar c, multiplying the zero scalar by any vector u should give us back the zero vector for the space. Any scalar multiplied by the zero vector for the space is equal to the zero vector for that space. And the negative of any vector, that is the additive inverse of a given vector, is equivalent to taking the scalar multiple of -1 times the vector u. All right. So now that we've defined a vector space formally, let's look at some standard examples for vector spaces that we'll use throughout this chapter and the remainder of the course. And in the majority of examples that we'll consider in our course, the addition and scalar multiplication operations are natural operations that we would consider on our set, such that the axioms 1 through 10 are easy to verify. We'll consider some strange examples a bit later in this section of spaces which are either are or are not vector spaces that have these sort of non-standard or or unnatural operations. But some of the examples that we'll work with most often have natural operations and are typical examples of vector spaces. We'll consider those here. So the most standard one would be the set Rn, which is the set of all n-dimensional vectors that have real entries. So as an example of an element of this set, we would have the vector x of n dimensions, so it contains n elements, x1, x2, up through xn, where each of these elements is a real number. So this is a non-empty set, and let's consider how we would define addition or scalar multiplication. So addition and scalar multiplication are defined in the standard ways. If we have two n-dimensional vectors, say x and y, whose components are given, and r is some real valued scalar, then vector addition, which would be denoted as the sum of x and y, is the n-dimensional vector where the ith component or ith element of that vector is the sum of the ith components of the individual vectors x and y. So we add them component-wise, exactly as we had defined in our earlier chapters. And scalar multiplication is defined as follows. So a scalar multiple of x would be the n-dimensional vector, where each entry of x is multiplied by that scalar r. So here we see right away that the sum and scalar multiple of these vectors would also be n-dimensional vectors whose entries are real, so it's closed under addition and scalar multiplication. And because of the associativity and commutativity properties of the real numbers, we have all of the other axioms for our vector space holding here. The only question is, well, for a given vector, how would we define its negative, or what is the zero vector considered for this space? So here we would define the zero vector for our space as the vector denoted as boldface 0, of length n, where each element in that vector is 0. And for any vector in our space, the negative of that vector would be denoted as negative of x, and it's the n-dimensional vector where each component of that vector is made negative. So this is a classic example of a vector space, is one of the most frequently considered as is the space Rn. Now another example of a vector space that we've already been working with would be the following. So here we're going to let M sub M by N of R denote the set of all M by N matrices which have real entries. So here our subscript in this notation is giving us the size of the matrix, or its dimensions, M by N, and this R expression is letting us know that the entries of our matrices are always real numbers. So as an example, we could have some matrix capital A whose ijth entry is denoted as lowercase a sub ij, which must be a real number. And we can define addition on this set in the standard way. So if A and B are two M by N matrices with real entries, and R is some real valued scalar, then the sum of two matrices, A plus B, is the matrix whose ijth entry is the sum of the ij entries of A and B respectively. And scalar multiplication of a matrix by some scalar R would be the M by N matrix whose ijth entry is R times the ijth entry of the matrix A. That is, we multiply every element or every entry of our matrix by that scalar. So the same sort of addition and scalar multiplication we've already been considering. Now for this vector space, the 0 matrix is denoted by capital O, and it would be the matrix where all entries are 0. That would be the 0 vector or the 0 matrix for this vector space. And the negative of any matrix is denoted as negative A, and it would be the matrix whose ijth entry is the negative of the ijth entry of A. So this would be another example of a vector space. It's easy to verify axioms 1 through 10 hold for the space defined in this way. Now some other classic examples. In our next example, we'll consider the space defined by R infinity, which would be the set of all infinite sequences or vectors, say, of infinite length, where the entries are real numbers. So we could consider, for instance, a infinite sequence or vector x, where we have infinitely many entries, x1, x2, x3, and so on, where each of these entries is a real number. So how can we define addition and scalar multiplication for these infinite sequences? Well, if we have two sequences, x and y, whose components are known, x1, x2, and y1, y2, so on, then if R is some real valued scalar, we can define the sum of x and y as the infinite sequence whose first term is the sum of the first terms of the sequences x and y. The second term would be the sum of the second terms of the sequences x and y, and so on. And the scalar multiple of a sequence x by some scalar r would be the infinite sequence whose first term is the scalar r times the first entry in that sequence x. The second entry would be r times the second entry of x, and so on. Now for this space, the 0 vector, or the 0 sequence, would be the sequence of all zeros. Every entry, or every component of that sequence would be 0. And the negative of a sequence would be defined as the sequence where each term in that sequence is the negative of the corresponding term in X itself. So these are some classic examples of vector spaces. Now we can also, which we've dealt with a little bit already in this course. We haven't really dealt with infinite sequences so much, but vectors or sequences of fixed length. So some other examples which are maybe a little more interesting or a little more complex would be the so-called trivial vector space, which is the set which consists of only the zero vector. So if we have a set consisting of only the so-called zero vector for a space, then we can define addition as the sum of any two elements in this set. Since the only element in our set is the zero vector, the only possible sum we could have is 0 plus 0, which is 0 itself. So it is closed under vector addition. And scalar multiplication would be defined as r times our zero vector, which is the only entry in our vector space, is equal to 0, which is itself in the vector space. So it's closed under scalar multiplication for any scalar r. And the negative of the zero vector is defined as negative of 0, which is 0 itself, because we've already seen if we add 0 to itself, we get back to 0. So the zero vector is its own additive inverse. So the vector space consisting of only a zero vector is known as the trivial vector space, and it is a vector space defined under these operations. Now for some other examples, we can consider spaces or sets of functions. So one of the easiest would be if we have a non-negative integer n, we could let p sub n denote the set of all polynomials of degree at most n. So as an example of such of an element of this set, we could take the polynomial p of t, which would have the form a0 plus a1t to the first, a2t squared, up through an t to the nth. So this would be a general polynomial of degree at most n. And these coefficients, a0 up through an, as well as our variable t, are taken as real numbers. So here, if we want to define addition or scalar multiplication, we would do it in the expected way. So if p of t is an nth degree polynomial with coefficients a, or say a sub I, and q of t is an nth degree polynomial with coefficients say b sub I, and r is some scalar, a real number, then we can define addition in our space as follows. So the sum p plus q of t would be the function defined as the sum of p of t and q of t. So combining coefficients according to the power of t, we would have a0 plus b0, the sum of the constant coefficients for our polynomial, plus a1 plus b1 times t, the sum of the t coefficients for our polynomials times t themselves, up through an plus bn times t to the nth. So we have the nth degree polynomial whose coefficient is the sum of the corresponding coefficients from p and q. And scalar multiplication would be defined as c times p of t, or c, so it would be the function denoted as c p of t, which is defined as the product of the scalar c times the polynomial p of t, which is found by taking each coefficient of our polynomial and multiplying it by that scalar c. Now, what is the so-called zero vector or zero polynomial for this set? Well, it would be the polynomial p of t, where all of our coefficients are 0. That is, a0, a1, a2, a3, and so on are all 0. Or we could think of it as specifically the constant polynomial whose only non-zero term is, or whose only term is a naught, where a naught is equal to the constant 0. And the negative of our polynomial, or of any polynomial in this set, would be denoted as negative p of t, and it's defined as the scalar negative 1 times p of t, which would be found by taking the nth degree polynomial, where each coefficient is the negative of the coefficient for p of t. Now we can define functions which are not just polynomials. So let's let capital F of r denote the set of all functions f which are mapping the real line onto itself. So capital F of r is the set of all functions of a single variable which are real valued. So if f and g are functions in f of r, and r is any real valued scalar, then addition of functions is defined as, so the sum of two functions, f and g, would be the function f plus g of x, whose value is given by the sum of f of x and g of x for every x in the real number line. And the scalar multiplication for this space would be defined as the function rf of x is equal to the scalar r times f of x for every x in the real number line. Now for this set of, or space of functions, the zero vector, or zero function, would be defined as the function 0 of x, which is equal to 0 for every value of x in the real number line. So it is the function which is always equal to 0 regardless of the input. And the negative of any function is the function negative f of x, which is defined as the negative of the value of the function f of x for every x in the real number line. So here we've got the set of all functions from the real number line to itself. If we want to restrict ourselves a little more to a certain type of function, we can use a different notation. For instance, C of r will be the set of all continuous functions, f from the real number line to itself. So if we want to specify that these functions must be continuous, we would use a different notation. And for this space, we could define addition and scalar multiplication in the exact same way that we would for the set of all functions from R to itself. The only thing that we have to be a little bit careful of when we're working with the space of continuous functions is we need to make sure that it is closed under vector addition and scalar multiplication. So for this space, we need to check that if f and g are two continuous functions from the real line onto itself, that the sum is also a continuous function, which is a result that you've seen in your calculus courses. The sum of continuous functions is continuous. And a scalar multiple of a continuous function is also continuous, which you've seen from, again, from your calculus classes. You've seen that the product of two continuous functions is continuous. So if we have a continuous function times a constant, well, we know that constant functions are continuous. Therefore, the constant times that function must also be continuous. So these are classic examples of vector spaces that we'll work with throughout this course. And it's fairly easy to verify that all 10 axioms hold for the vector spaces that we've discussed so far, based off the way that addition and scalar multiplication are defined. So let's look at some counter examples. So what would be examples of sets that we could consider with operations, say vector addition or scalar multiplication, which would not satisfy all 10 of these axioms? So the first of which is if we're taking some restricted space of a known vector space. So as an example of this, let's consider the set W, which would be the union of the first and the third quadrants of the xy plane. So that is, W is the set of all points in the xy plane such that the product of x and y is non-negative. So let's visualize this space here. So W is the part of the xy plane, which consists of the first quadrant, so points where both x and y are positive, and the third quadrant, points where both x and y are negative, so that the product of x times y for points in either quadrant must be non-negative. Now specifically here, we're taking the possibility that x times y could be equal to 0, so x or y could equal to 0, so we're including the points along the x and y axes in addition to those shaded quadrants. So this is our set W. And we would define the standard addition and scalar multiplication for these points. And in part A of this problem, we are asked to show if U is a vector in this space and C is any scalar, is C times U in W, and justify our answer. So that is this space W closed under scalar multiplication? So let's consider that. Here, let's choose some vector U be in W. So it's some point xy, which lies in the set W, which means that its components, or let me maybe call the components something other than arbitrary x and y. So let's take a vector U whose components, let's call U1 and U2, be a vector in this space W. So that means that the product of those components, that is U1 times U2, must be non-negative. That was the definition of this space W. Now, if we're looking at a scalar multiple of the vector U, well, using the standard scalar multiplication for vectors, that means that we're taking each component of our vector and multiplying by the constant or the scalar c. So we're going to have the vector cu1 and cu2, and the question is, does this lie in the set W? So the check would be to take the product of the entries of this vector, that is c times u1 times c times u2. So we would have c u1 times c u2, and using the associativity of a product for real numbers, we could rewrite this as c squared times u1 u2. And we know that the first term, c squared, is always going to be non-negative for any scalar c, any real number. If you square it, it's at least 0. and the product u1 times u2 had to be non-negative since u was a vector in this space. So the product must be non-negative since c squared is non-negative and u1 times u2 was non-negative. So we've established that the scalar multiple of any vector in W must also lie in W. All right. So this space is closed under scalar multiplication. Now, in part B of this example, we are asked to find specific vectors u and v in this space W, such that the sum u plus v is not in W. So it turns out this space is not closed under vector addition. So let's try to find examples of vectors u and v such that the sum would not be within our set. So there's many examples that we could consider. As one possible example, we could consider a vector u, say for instance 3, 1, and a vector v, so here u lies in my first quadrant, so I'm trying to find vectors such that the sum would not lie in the first or the third quadrant. So I want one of my components in this sum to be positive and the other to be negative. So an easy way to accomplish this is to take the sum of, say, the first components of these two vectors as two numbers that yield a positive value. So say 3 and negative 2 would give us a positive 1. And I want the sum of the second components to be a negative value. So if I chose 1, I could use negative 2 or any negative number whose magnitude is greater than 1. And we find that the sum of u and v would be 1, negative 1. And the product of these entries is negative 1, which is not greater than or equal to 0. So we've shown that while the vectors u and v lie within the set W, that is the product of their components are both non-negative, the sum has a product which was negative. So here u plus v does not lie in this set W. So in part C of this example, we ask the question, well, is W a vector space, and explain. So the answer to part C is no. W is not a vector space since it is not closed under addition. So in particular, axiom 1 fails for this space. Axiom number 1 in our definition for vector spaces was that the space must be closed under vector addition. If you take any two vectors in the space, the sum must also lie in the space. But we've shown in part B of this example that that is not true. Therefore, by definition, this cannot be a vector space. All right. So here's one example of a set that would not be a vector space. Now our next two examples introduce sort of non-standard operations on a familiar set of vectors that would show in using these non-standard operations that we would not have a vector space. So our first example that we'll consider has a new definition of scalar multiplication, which we'll refer to as dumb scaling. So here, let's suppose that V is the set Rn, so the set of n-dimensional vectors with real entries. And we'll assume that this space has the standard addition for n-dimensional vectors, but we will define a non-standard scalar multiplication in the following way. So for any scalar r, some real number, I'm going to define a non-standard scalar multiplication as follows. So r, and here since I'm using a non-standard operation, I'm going to use the symbol circle dot to denote the non-standard multiplication operation. So r circle dot x is defined to be the zero vector for any vector x and any scalar r. So taking the product of any scalar and any vector in my space, I'm going to define that as the zero vector for my space. And our problem here is to show that this space V is not a vector space. So let's consider which of the axioms fails here. Now we know that our space has the standard addition operation. So the first 6 axioms that deal with addition within my vector space all hold because we're using standard addition on Rn. But the last few properties that involve scalar multiplication with this non-standard product, one of those is likely the culprit. So let's consider axiom 7 to start with. The first axiom dealing with scalar multiplication, which is asking the question, well, does a scalar r times, using this dot times operation, or circle dot scalar multiplication operation, with a sum of vectors, let's say x plus y, is that equal to the sum of the scalar multiple of r with x and the scalar multiple of r with y? So we want to know, is this true? Now, based on the definition of this non-standard product, on our left-hand side, no matter what r and x and y are, this scalar product is defined to be the zero vector. Now, on our right-hand side, we have, first of all, a product of a scalar r with a vector x, which using our definition is defined as the zero vector. And then we have the sum of a scalar r with a different vector y, but regardless of what the scalar and vector are, we were always defining this scalar product as the zero vector. Now, based off the definition of the zero vector, on this right-hand side, if I'm summing the zero vector with anything else, I get that other vector, in this case the zero vector. So this axiom 7 does hold true, using this odd definition of a scalar multiple. So let's look at another one. Axiom 8 was the following. If we have two scalars, let's say r and s, and I'm taking their sum and applying that scalar multiple to a vector x, is that equal to the sum of the scalar multiple of x by r and the scalar multiple of x by s? Now, the way that we've defined this scaling is so that regardless of what our scalars and vectors are, this odd multiple is always the zero vector. So on our left-hand side, we have the zero vector, and each of these terms on the right-hand side are circle dot x or s circle dot x. It doesn't matter what the scalars or the vectors are, they're always defined as 0. And again, using the fact that the zero vector plus any vector must be the zero vector, our right-hand side reduces to the zero vector, so axiom 8 also holds. So let's look at another one. Axiom 9 is considering the following. If we take a scalar multiple, using this weird product definition, of a scalar multiple of a vector x, is that equal to the product of the scalars r and s, and taking that scalar multiple of our vector x. So let's take a look at this. We have, for the scalar multiple of x by the scalar s, the 0 vector, and on our right-hand side, regardless of what this scalar r times s was, or what the vector x was, using this product, we have the 0 vector as that product. So for our scalar multiple on the left-hand side, regardless of what our vector was, in this case 0, any scalar multiple of a vector is defined to be 0 itself. So Axiom 9 also holds. So let's consider our last axiom involving a scalar multiplication of a space. So the last axiom was if you take the scalar 1 and take its scalar multiple of a vector, you're supposed to get back the same vector x. Now on our left-hand side, using this dumb scaling, where regardless of what our scalar and our vector are, we define the product to be the 0 vector. We have 0 is equal to x, but that does not hold for every vector x. For axiom 10 to hold, 1 times x must equal to x for every vector x. We see here that would only hold true if x were the 0 vector. So since axiom 10 fails, this space V is not a vector space. By using this non-standard multiplication that we would refer to as dumb scaling, we see that it does not satisfy all axioms for our vector space. So let's look at another one. In this next example, we've got something very similar, where we will have a set V, which is the set of all n-dimensional vectors of real numbers. And again, we're going to use the standard addition for that space, but we will use a non-standard scalar multiplication defined as r dot times x, or circle dot x, is equal to x for every x in the space and for every scalar r. So that is regardless of what scalar we multiply our vector by, we're going to get the exact same vector x. So for this space, we want to show that V is not a vector space. One of our axioms fails. So let's consider which one fails here. Again, since we're using the standard addition axioms 1 through 6 that involve scalar, or that involve a vector addition automatically hold, since we know we're using standard addition on the space Rn, and we've already established that is a vector space. So let's consider the axioms dealing with multiplication. So here, axiom 7 is again the axiom where if I'm taking a scalar multiple of a sum of vectors, x plus y, using this odd vector operation, I should get back the sum of the scalar multiples of x and y by the same scalar r. So using our definition, on the left-hand side, regardless of what r is, when I'm taking a scalar multiple of a vector x plus y, using this odd definition, we take the exact vector x plus y. And on our right-hand side, well, r dot times x is defined as exactly the vector x, and then we're adding our circle dot y is exactly the vector y. So we see that this does hold, axiom 7 holds for this lazy scaling. Let's move to our next axiom. Axiom 8 says if we're taking a scalar multiple of a vector x, where our scalar is a sum of two scalars, say r and s, is that equal to the sum of the scalar multiple of x by r and the scalar multiple of x by s. So using this lazy scaling, the left-hand side, regardless of what the scalar is, if I'm taking a multiple of x, I just get x. And on the right-hand side, well, if I'm taking a scalar multiple of x by r, it's defined as x. And then we are summing a scalar multiple of x by s, which is again defined just as x. So we see here that x would not be equal to the sum of x with itself for every vector in our space. When we're using the standard addition, our right-hand side, x plus x, is equivalent to scalar multiplication of x by 2. So we see here that axiom 8 fails. And so our space V is not a vector space. So in this first part of our section 4.1 lecture, we've defined a vector space. Again, it is a non-empty set of elements called vectors with two operations known as addition or scalar multiplication that satisfy 10 axioms or 10 properties. And we've looked at some classic examples of vector spaces, namely spaces of n-dimensional vectors, m by n matrices, polynomial functions, real-valued functions, continuous functions, in infinite sequences of real numbers in a trivial space consisting of only a zero vector. So some classic examples of vector spaces. And then we've seen some counter examples of certain spaces where if we define one of our operations, like scalar multiplication, in a non-traditional way, we see that maybe one of our axioms does not hold. Or we had seen one example where we had a set of points in the plane, but where that set of points was maybe not closed under one of our operations, like vector addition. So in the next part of our section, which will be our next lecture, we'll start discussing something known as subspaces.